let us understand some of the properties of generator polynomial. Now generator polynomial is a special polynomial and it's the key to perform all the operations, that is encoding and decoding, for cyclic code. So generator polynomial has three basic properties. First thing, the degree of generator polynomial is always n minus k. So g of x is a unique lowest degree non-zero polynomial with a degree n minus k. This is the first property. Second, every code word is some multiple of generator polynomial. So you can say that when any code word is there that is divided by generator polynomial, we get remainder as 0 because this g of x is one of the factor of code word polynomial, and this property we are going to exploit for the process of encoding and decoding. And the last property is this generator polynomial is always a factor of a polynomial x raised to n plus 1, where n is the length of the code word. So depending on the length of the code word, you will have a generator polynomial. Again, generator polynomial is a factor of x raised to n plus 1. These are the three properties of generator polynomial, which we will be studying in more depth while studying BCH and RS code. For a time being, we will be using these properties directly. In this slide, we are going to again define the same concept, cyclic code, its shift, representing it in the form of polynomial and all that. Only the changes, previously we were calling it as code polynomial c of x, that is code is represented by c and polynomial in terms of x. Here we are representing code as x and the polynomial in terms of p, so it is x of p rather than c of x. Now in this slide we are using x of p as the representation. Hope you people will not get confused due to this representation. So it's only a polynomial representation where x represents the position of the code word bits and p represents the degree. So p is the variable in this case and x represents the code bits. So let us start with encoding of cyclic code. So to generate a cyclic code 7,4 using a non-systematic way, we use a simple process of polynomial multiplication. Let's say that for 7,4 code, the generator polynomial is p cube plus p plus 1, the one which we have seen in a last slide in the form of x. Here we are representing it in the form of p. That's the only change. So generator polynomial g of p is equal to p cube plus p plus 1, and whichever message we want to convert into the form of code word, we just multiply this generator by a message polynomial. So what we do is, first we take a message and convert that message in the form of polynomial. So let's start with the process of encoding. So here m is equal to 1101. So my message is this. So my message is a 4-bit. So when I convert it into the form of polynomial, the degree will be 1 less than the number of bits. So here, as I am having 4 bits, the degree will be equal to 3 or less than that. So here it will become p cube plus p square plus 1. So as you can see that the bit 0 is at the position 1, that is p raised to 1 should be there, but as it is multiplied by 0, it will get cancelled out. Hence only the 3 ones are there. So these 3 ones are represented by p cube as the first bit, p square as the second bit, and the last bit will be represented as p raised to 0, that will be equal to 1. Hence my message polynomial becomes p cube plus p square plus 1. And this is supposed to be multiplied by generator polynomial, that is p cube plus p plus 1. So again p cube is there, so this should have 4 bits. Hence this generator polynomial in the binary form is represented as p cube position is 1, p square is absent, so it is 0, p is present 1, and 1 is present, that is 1. So that's why generator polynomial is represented as 1 0 1 1. So we have In the first case, for message is a binary form, we convert into polynomial. In the second case, generator is in the polynomial form, we convert it into binary form. Now let's multiply this message with the generator polynomial, because as we have seen the properties of generator polynomial, that every code is some multiple of generator polynomial. That means to get a code word, we should multiply message polynomial with a generator polynomial. So here we have m of p will be multiplied with g of p. So that's why the first term will be p cube plus p square plus 1. This will be multiplied by p cube plus p plus 1. And when we perform this polynomial multiplication and use a modulo 2 addition, you can understand that p cube occurs thrice in this addition, and because of that p cube 2 times p cube will get cancelled out. So p cube plus p cube will get cancelled out and only one p cube will remain. And we will have a code polynomial as p raised to 6 plus p raised to 5 plus p raised to 4 plus p cube plus p square plus p plus 1. When we convert into the form of binary representation, as every power of p is present, it will be written as 1 1 1 1 1, that is 7 ones are there. Now your message was 1101, and you can understand that message is completely missing in this code. So you can't figure out your message from this code polynomial. Hence it is called as non-systematic code. What we have defined in the systematic code is a code in which parity bits and message bits are easily separable. So message is a part of the code. Then it is called as systematic code. In this case, message is there, but it is completely scrambled. So I can't figure out which bits represents message. Then that code is called as non-systematic code. So this is the first example of non-systematic code. So the process of encoding for non-systematic code is quite simple. Simply take a message polynomial and generator polynomial, multiply them together, you will get a code word polynomial. Second operation which is represented is of the same form, that you have x cube plus x square plus 1, that is your message polynomial, multiplied by generator polynomial x cube plus x plus 1, and you can understand that it's same as the above answer. So just to have the what uniformity between what we have seen previously and right now, because we are shifting from x to p, we have just represented both the processes or both the way representation on this slide. It's not different, it's the same one. So the code words are same. So the final takeaway from this slide is a non-systematic code is one in which message bits are scrambled. This is the first thing, and I can't figure out which bits of the code word represents my message bit in it. Second point is, to generate a non-systematic code, we are supposed to multiply message polynomial with a generator polynomial. Okay. So here we completed non-systematic encoding. Now we will understand one important operation in the form of polynomial, that is cyclic shift in the form of polynomial. So to have a cyclic shift by using polynomial operation, what we are going to do is a polynomial x will be first multiplied by p, and that will be divided by a term p raised to n plus 1. In the process of division, the remainder will represent the cyclic shifted code. So here the theorem is, a single cyclic shift of x is obtained by multiplication p into x, where after division by the factor p raised to n plus 1 yields 1 bit cyclic shifted code at the remainder. So this process is represented mathematically as x dash p, where that dash represents 1 bit cyclic shift. So x dash p is equal to p into x of p mod of p raised to n plus 1. So if I want to perform I bit cyclic shift, as in the previously we have seen 1 bit cyclic shift, we multiply the code polynomial by p if I want to perform I-bit cyclic shift, I have to multiply it by p raised to I and again divide it by the polynomial p raised to n plus 1 and remainder will yield into the cyclic shifted code. So x raised to I of p is equal to p raised to I xp mod of p raised to n plus 1. Let's understand the whole process by using one example. Let's say that we are having a 3-bit code 101. As the code is of 3-bit, the degree maximum power of the polynomial will be 2. Hence the code polynomial is represented as x of p is equal to p square plus 1. So the middle term which should be represented by p is absent because the coefficient related to that is 0. That as we have got only 2 ones, we have got p square plus 1. Now to perform a cyclic shift, multiply this polynomial by p. So that's why p into x of p is equal to p cube plus p. Now as the process says, divide this by p raised to n plus 1. So in our case n is equal to 3. That's why divide this p cube plus p by p cube plus 1. So p into x of p divided by p cube plus 1. So the division you can see is done on this slide. On one side, that is on the right hand side, we are performing a division. P cube plus p is divided by p cube plus 1. So quotient is 1 and the remainder is p plus 1. So what is, we are interested not into quotient, we are interested in the remainder. So this remainder is p plus 1 represented by 3-bit. So as p square is absent, it will be 0 and p and 1 are present will become 1 1. So we have got code as 0 1 1. So if you look at the relationship between 101 and 011, you will understand that the code is left shifted by 1 position. So this polynomial process represents a 1-bit cyclic shift to the left by using power of p and modulo 2 operation. So the important point is, if we want to implement this, how we are going to implement it in the hardware? So it will be implemented simply by using a tap shift register. That means by using a shift register where some taps are required which represent some kind of modulo operations here. Okay? So this process is cyclic shift in the form of binary, polynomial by using a polynomial, and third by using hardware. Likewise, 3 things are there which one has to understand. Okay? So we will use this case, or we will use this mathematics for further examples where we will be using systematic codes. We have seen in previous slides that every code word polynomial is some multiple of generator polynomial, or in other words, generator polynomial is one of the factor of code word polynomial. So the theorem says that cyclic code polynomial x can be generated by multiplying a message polynomial m of degree k minus 1 by a generator polynomial g of degree n minus k, where g is qth factor of p raised to n plus 1. So this is the third property of generator polynomial, that generator polynomial is a factor of p raised to n plus 1. So let's understand this mathematics, and it tells us how to represent a code in a systematic form. So this mathematics will lead us toward encoding process and representation of a code word in the form of polynomial. So let's say a message polynomial is there which has got k bits, so it can be represented, or message word is there which has got k bits, so that can be represented by a message polynomial of degree k minus 1. So MP represents a message polynomial. Now we may have a code word polynomial which is xp. So this code word polynomial has degree n minus 1, or in other words, the code word has got n bits. So what we have seen is this xp, that is code word polynomial, is multiplication of message polynomial into generator polynomial. So it is m of p into g of p. So every term of message polynomial is multiplied by g of p. So you can take g of p common and you will get a code word polynomial. So let us understand now that how a shifted code is again a valid code word. So for this we are going to use a concept that every code word is a multiple of generator polynomial. So let's say p into x of p is there. So x of p is a code word polynomial which has got degree n minus 1. When it is multiplied by p, every p power will be incremented by 1 and p into x of p is a polynomial having a degree n. Now to make a degree again as n minus 1, what we will do is we will add x suffix n minus 1 twice. So you can see that x suffix n minus 1 is added in the last term as well as in the first term. So x of n minus 1 when taken common from p raised to n, we will get that it is x of n into bracket raised to pn p raised to n plus 1, and the second bracket, if you look carefully, it represents a 1-bit cyclic shift of a code word polynomial. Now this is x dash p, and the term that remains is xn x suffix n minus 1 into p raised to n plus 1. Now p raised to n plus 1 has one of the factor as generator polynomial. X dash p is a shifted code, so that also has a generator polynomial in it. So we can say that the overall term p into x of p is equal to p into message polynomial into generator polynomial. So here what we can say is x dash p is a valid code because p into x of p represents a cyclic shift. So as per a cyclic shift, every cyclic shifted code is again a valid code. So here we can say that x dash p must be a multiple of generator polynomial, which we proved above. And if this x dash p is represented as some message m1 multiplied by generator polynomial, then x dash represent a code vector for corresponding message vector m. So it means 1-bit cyclic shift represent a code word polynomial for some other message than message m. So for message m, if there is a code vector x, for message m1 there will be a new code word vector x dash, which is a shifted code. So if we perform this shift for I is equal to 1, 2, 3, 4 and so on, every time we will get a new code word which will represent some another code word m. And as we have seen that every code word is multiplication of message polynomial and generator polynomial. So it simply says that the shifted code are valid code word for some of the messages, or every shifted code word represents a different code word for different messages, as there is one-to-one correspondence between them. So what we have seen in the last slide, same is carried forward here. P into xp represents a 1-bit cyclic shift, and which is nothing but x dash p, which is message multiplied by generator into p. So it represents a p-bit cyclic shift of the message, which is called represented as m1. So p into x of p is a code word for message m1. So cyclic shifted code is again a valid code for some message m1. So every cyclic shift will give you a valid code for some other messages. This slide represents how to get a generator polynomial. So we have seen that generator polynomial is always a factor of p raised to n plus 1 or x raised to n plus 1 with a degree n minus k. So here we consider a code with n is equal to 7. So p raised to 7 plus 1 is the polynomial. When we factorize it, we will get a 3 factors of it, p plus 1, pq plus p plus 1, and pq plus p square plus 1. So both the factors, that is pq plus p plus 1 and pq plus p square plus 1, can be used as a generator polynomial, as both are irreducible polynomials and they are having a degree n minus k in this case. So how we utilize them? So to get a code word, we multiply a message with a generator polynomial. So here we are having a message p square plus 1. So p square plus 1 will be represented as a message 0 1 0 1, and when it is multiplied by a generator polynomial pq plus p plus 1, we will get a corresponding code word polynomial p raised to 5 plus p square plus p plus 1, which is represented as 0 1 0 0 1 1. So this represents a code vector for it. So it represents that n minus k is equal to 3, and we can use that as a generator polynomial. So this is just a simple method to get a generator polynomial for cyclic code. This slide represents a table which represents or which are having generator polynomial for different order of codes. For example, the first row represents a 7,4 cyclic code which has got 1 bit error correction capability, so d minimum is equal to 3, and in that case your code rate is equal to 0.57. If you see the generator polynomial, it has got bits 1 0 1 1, and when converted into the form of polynomial, it is represented as gp is equal to pq plus p plus 1. So likewise you can have different order of cyclic codes, that is 15, 11, 31, 26, 15, 7, 31, 21, 63, 45. So for all these different order codes, they are having different error correction capabilities, and n minus k values will keep on changing. So accordingly your generator polynomials will also keep on changing. So these are the few of the examples of generator polynomial which mathematicians have already derived for us, and the same we are going to derive in next unit, that is BCH codes and RS codes. So this is just for your reference that how the generator polynomials are available. So now we will start with systematic cyclic code. To have a better understanding of this systematic cyclic code, first we will recall the definition of systematic code. So systematic code is one in which the message bits and parity bits are easily separable, is called as a systematic code. So if you can see in the information given in the red color, we have taken a message 1001, and when we convert that message into the form of systematic code word, we have got first 4 bits which is 1001 as the message, and the last 3 bits are 110 which is parity bits. So a systematic code is one in which message bits and parity bits are easily separable, or message bits form a one separate part of a code word. So when we represent this in the form of polynomial, as message has got 4 bits, it will have a degree 3. So message polynomial is mp is equal to pq plus 1, and when we represent that in the form of code word, the code word polynomial will be c of p is equal to p raised to 6 plus pq plus p square plus p. So here if you see, your message bits are 1001 is represented in the polynomial form as p raised to 6 plus p cube, whereas the actual message is p cube plus 1. And the code that we consider here is a 7,4 code. So n minus k value is 3, and you can understand that a message polynomial is multiplied by p raised to 3. So if you understand this concept, now we can make it a generalized one. So let's go to have a generalized concept. Let's start from the starting of this slide. So here define a length q is equal to n minus k. So the number of parity bits are n minus k, and the check vector that is called as parity vector is defined as c. Let the length of the message is k bit, then the message polynomial is mp and it has got degree k minus 1. Then check vector or parity bits has got degree n minus k minus 1 or simply q minus 1, because n minus k we consider as q. Now for systematic code, this message polynomial and parity bit polynomial, they are clubbed together. But we want them to be separated. That's why the message polynomial is multiplied first of all by p raised to q. That means the degree of message polynomial is incremented by the value of p raised to q. As in the example, we incremented the degree of message polynomial by 3. In the generic manner, we increment the degree of message polynomial by n minus k for systematic code. So that's why the systematic code xp is given as message polynomial mp into p raised to q plus cp. So this is the form of systematic code. Please remember, xp is equal to p raised to q into message polynomial plus cp represents your code word polynomial in a systematic form. Now let us derive the procedure for systematic cyclic code encoding. So here what we are going to do is, let's represent the code word polynomial in its different form. That is, the code word polynomial xp is multiplication of message polynomial and generator polynomial. This is the first definition that we have seen from the properties of generator polynomial. And second one that we have seen in the last slide using systematic code, that every systematic code is represented as message polynomial into p raised to q plus check bit polynomial c of p. So we got this definition: m of p into g of p is equal to p raised to q into mp plus cp. Now this equation will lead to the encoding mathematics. So what we are going to do is, let's make a small adjustment in this. For both the terms, add cp in it, as it's a modulo 2 addition. cp plus cp will become 0. So what we have is only p raised to q plus mp on the right hand side, and on the left hand side we will have mp message polynomial into generator polynomial plus cp. Now to this equation, divide by generator polynomial. So what we have right now is p raised to q into m of p divided by g of p is equal to m of p plus c of p divided by g of p. This is basically equation of polynomial division, where p raised to q into m of p represents a dividend, g of p represents a divisor. So m of p represents a quotient and c of p represents a remainder. So what we are interested is in the check bits c of p. So this tells us a simple concept that we can get a check bit polynomial or c of p by using the procedure as follows. So the step number 1 is take a message bits, represent it in the polynomial form. Second, multiply this m of p by a term p raised to n minus k or p of q, p raised to q. Whatever this polynomial we will get, p raised to q into m of p divided by generator polynomial and find the remainder. This remainder is nothing but our check bits, and to get a systematic code word, add this c of p with p raised to q into m of p. That will give you a systematic code words. So what all steps I have just described or narrated to you, let's follow them for one example. So here we are having a generator polynomial for 7,4 code as pq plus p square plus 1. Now we are using a message polynomial, that is pq plus p, or message is 1010. So 1010 is the message which we want to convert into a systematic code. So let that message is multiplied by a generator p raised to n minus k. So in this case it is supposed to multiply by p raised to 3. So p raised to 7 minus 4 into m of p will become p raised to 6 plus p raised to 4. Please ignore the sign because here addition and subtraction both are treated as same. Now multiply this term p raised to 6 plus p raised to 4 by generator polynomial pq plus p square plus 1. So you will get a quotient part which is pq plus p square plus 1. Ignore that, and what you will have is a check bit which is equal to 1. Now add this 1 into the term p raised to n minus k into m of p, which is p raised to 6 plus p raised to 4 plus 1. So what we will have is the code word polynomial as 1 0 1 0 and 0 0 1. So that becomes our systematic code. Let's continue with the example of cyclic code. Now let's consider again a 7,4 cyclic code where a message is 1100. So let's continue solving this example step by step. So first step is represent this message in the form of polynomial. So as it's a 4-bit message, the degree of polynomial will be 3. Therefore message polynomial will be p cube plus p square, and the last 2 bits are 0. So therefore p plus 1 terms will be absent in this case. For 7,4 code, n minus k will be equal to 3. So in the step number 2, we multiply message polynomial by p raised to 3. So that means increase the degree of or power of every term of p by the value of 3. Therefore p cube into mp will become p raised to 6 plus p raised to 5. Third step tells us that whatever this polynomial we get, p raised to q into m of p, divide that by generator polynomial. So for 7,4 code, we have chosen generator polynomial as p cube plus p plus 1. So divide this polynomial p cube into m of p, that is p raised to 6 plus p raised to 5 by p cube plus p plus 1. So in the next step you will understand how we perform the polynomial division, and finally the remainder comes as p. So we are not interested into quotient, we are interested into remainder. So remainder is p. So let's add this remainder to the next to the term p cube into m of p. So let's understand that in the next slide. So if we add this remainder c of p into p raised to q into m of p, we get a code word polynomial. So in our case, p cube into m of p is p raised to 6 plus p raised to 5, and we add c of p, that is p in it. So we get a code word polynomial as p cube plus p raised to 5 plus p, and represent that again into a binary form. So a p raised to 6 is there, so that term will become 1, p raised to 5 again 1, 4 and 4, 3 and 2, these powers are absent, therefore then that will be 0. P raised to 1 is there, so that will become 1, and p raised to 0 is again absent, so that's why it will become 0. So if you can see that the first 4 bits are your message bit and last 3 bits are parity bit. Thus we get a systematic code or systematic cyclic code by using a polynomial division. So please understand this procedure. This is one of the example for you people. You can try out some other examples, or you can take other messages, convert them into the form of polynomial and generate the cyclic codes for it. You just have to see that the first 4 bits will be always your message and the last 3 bits will be parity. So this is systematic encoding of cyclic code. Here is one more example of cyclic encoding. So we have used a data word x cube plus 1, and that we encoded in a systematic manner. So as you can see, from x cube plus 1 we incremented its power by 3, so we got x raised to 6 plus x cube, and divided it by generator polynomial to calculate remainder. So the remainder we add again with the dividend x raised to 6 plus x cube, so which will generate the required code word polynomial, which is x raised to 6 plus x cube plus x square plus x. So this is all about the encoding process in a polynomial form. Here we are representing the same process of cyclic encoding by using the binary division. So previously we have seen encoding using polynomial division or systematic cyclic code encoding by using polynomial division. Now we are using the same encoding process but in the form of binary division or using binary division. So what we are going to do is data word is x cube plus 1, which is represented by 1001, and as we are supposed to increase its degree by 3, we append 3 zeros to it so that the degree will be incremented by 3. And now we perform a binary division for it, and you can understand that the remainder that remains, or the remainder, is 110. So we are going to append that remainder with the message bit. So message bits is 1001, and then we append 110. That becomes a code word for us. So it's not necessary that we should always convert the given polynomial or given message into the form of polynomial and then only perform the polynomial division. We can do it by binary division also, and this is what precisely we are doing in the shift register encoding process, that is in hardware. Now let us verify the fact that if a code word polynomial is there and this code word polynomial is divided by generator polynomial, we should get remainder as 0, because in the properties of generator polynomial we have seen second property as every code word polynomial is some multiple of generator polynomial, and we have used this concept to get a non-systematic code. But for systematic code we have used completely different approach, where we have used polynomial division. We calculated a remainder and we add that remainder with a shifted message polynomial. So this polynomial or code word polynomial, when it is divided by generator polynomial, are we really getting remainder as 0, so that we can claim that yes, this code word polynomial has generator polynomial as one of its factor. So here we have taken a generator polynomial, that is p cube plus p square plus 1. You can even choose p cube plus p plus 1 and you can generate a code word for it. So let's take a message which is 1010 represented as message polynomial p cube plus p. Let's increment its degree by 3, so we get p raised to 6 plus p raised to 4. So divide this incremented polynomial degree or incremented degree polynomial with a generator polynomial, and we calculate the check bit. So here the check polynomial is 1. Let's add that check polynomial with the shifted degree message polynomial so as to get a code word polynomial. So you can see that the code word polynomial is right now p raised to 6 plus p raised to 4 plus 1. Now to verify whether this has a generator polynomial as one of the factor or not, let's divide this polynomial by generator polynomial. So when we perform the long division method for these polynomials, we will understand that the remainder becomes 0. So we can understood that the generator polynomial completely divides this polynomial. That means generator polynomial is a factor of this code word polynomial. And this concept or this fact we will be using for the process of decoding in the upcoming slides. So hope this concept is clear for you people. Now let's start with the process of decoding. So for linear block code decoding, we have seen two approaches. One is a standard arrow decoding and second one is syndrome decoding. So here we will be concentrating only on syndrome decoding because that's the easier approach, or as far as implementation is concerned, it's easier to have syndrome decoding. So here the fact that we have seen in last slide, that every code word polynomial has generator polynomial as one of its factor. So whenever a code word polynomial is divided by generator polynomial, we expect remainder to be 0. So what we do in the decoding process is the received polynomial r of p, we divide it by generator polynomial, and if we get remainder 0, we claim that there is no error during the process of transmission takes place and the received polynomial is same as the transmitted polynomial. But if we get some non-zero remainder, that means we calculate a syndrome. So here by dividing generator or received polynomial by a generator polynomial, what the remainder we get is called as syndrome. So if the syndrome is non-zero, we claim that there is a error. Here is a basic mathematics behind it. Let's say that received polynomial RP is equal to actual code word polynomial XP plus error polynomial EP. So received polynomial is code word polynomial plus error polynomial. So when we perform this division, the remainder we called it as syndrome, which is denoted here as SP. So SP is equal to X of P plus E of P divided by G of P. So when we use again a modulo n plus 1 mathematics here, and due to that, when XP is divided by generator polynomial, where we will be getting 0 as a syndrome. But when error is divided by generator polynomial, if error is non-zero vector, then we are sure that syndrome will also be a non-zero vector. So again, it clarifies the concept that we have seen in syndrome decoding, that the syndrome depends only on the error and not on the transmitted code word. So this is all the procedure about calculating a syndrome. So how we are going to calculate a syndrome? We will take a received polynomial and divide it by generator polynomial, and the remainder whichever is there, that we are going to call as syndrome polynomial. To start the syndrome decoding or decoding of cyclic code, what we require initially is a syndrome decoding table. So it has error patterns and it has syndromes. So how we calculate these syndromes? So the way we have seen the syndrome or error patterns in cyclic code, in the same manner we will first understand what is the error correction capability of the code is. We write down all possible error patterns which can be corrected. So in this case, for 7,4 code, it has got 1 bit error correction capability. So we have written down all the possible error patterns which has got 1 bit in error, and convert that error pattern into its polynomial representation. Whatever the error pattern is there, divide that error pattern with the generator polynomial which we are using for the process of encoding and decoding. After division or long division process, whatever remainder we get, that remainder we are going to call as syndrome. Now you can cross check in the example that we have used here a generator polynomial as x cube plus x square plus 1, and for this 7,4 code, it has got 1 bit error correction capability which is shown in the table. So let's start with the first error pattern. So the first error pattern is 1 and all remaining zeros are there. So this error pattern E of x will be represented by x raised to 6. Let's divide this error polynomial x raised to 6 by a generator polynomial x cube plus x square plus 1. Using a long division method, you will understand that the remainder that finally comes is x square plus x, and when we convert it into the binary form, it becomes 1 1 0, because x square plus x plus the next term should be x raised to 0, that is 1, which is missing, hence that last bit will become 0. So the syndrome becomes 0. You can do this for remaining error patterns. Like a second error pattern is 0 1, and all remaining zeros will be represented by x raised to 5. Next will be 0 0 1, remaining zeros will be represented by x raised to 4, and so on, and divide this error polynomial by generator polynomial to calculate the syndrome. This will gives you all possible syndromes and error pattern, which we called as syndrome decoding table or simply syndrome table. So now we are ready with a syndrome table, and we can understand or decode any of the received code, which we will understand in next slide. Now let us start with actual decoding. As we have syndrome decoding table ready, so we can perform the decoding of the received code. Let's say that the received code that we have is 1101101. Now let's represent that received code in the form of polynomial. So the bits which are having 1, their position will be represented by x power, and those which are having zeros will be cancelled, or we will ignore them. So the first bit is 1, so it is x raised to 6. Next is again 1, x raised to 5. Next is absent, so x raised to 4 will not be there. So x cube is there, x square is there, again x will be absent, plus 1. So this is the received polynomial x raised to 6 plus x raised to 5 plus x cube plus x square plus 1, and divide this received polynomial with a generator polynomial x cube plus x square plus 1 to calculate a syndrome. The remainder will be our syndrome, which we represent here as mod. So once we perform the polynomial division, we will get that the syndrome is x square plus 1. So x square plus 1, when we convert into the binary form, only x power is missing, so it will be 1 0 1. So 101 is the syndrome, and now let's go to the syndrome decoding table. So you will understand that it's syndrome number 4, which is 101, which claims that middle bit is in the error. So take that corresponding error polynomial, which is 000 1 000, and XOR that with the received code. So corrected code is equal to received code plus error. Procedure is same as what we have seen in linear block code, and what we get is the corrected code, which is 1100 101, and the first 4 bits of it are message bits and the last 3 bits are parity bits. So as we are interested in message bits, so the decoded message bits is 1100. In the similar manner, you can go for following received code or received words, and you can calculate syndrome for them and find out the corrected code. So you can keep this as a homework for you and try out it. Answer is with you. You just have to perform polynomial division and cross check your answers. As for encoding, we have seen a polynomial division can be used for encoding, as well as binary division can also be used for encoding. Same method we followed for decoding also. First of all, we have seen decoding or syndrome calculation using polynomial division. Now we have same syndrome calculation for using binary division. So we have a received code, and to that received code, when we divide it by generator polynomial, we try to calculate the remainder. So for the first division, you can see that syndrome is 0, which claims that there is no error, and the first 4 bit represents your message or data words. The same code when received with an error, as you can see that the fourth position 1 is converted into 0, which is given as given in a red color, and if we perform a binary division, in this case your syndrome becomes non-zero. So what a simple ARQ scheme can be: we will discard this received data word and we ask the transmitter to retransmit it, so that will become a ARQ. And if we have a syndrome decoding possible, we can go ahead and try to decode the received code.